Welcome to this video on current transformer vector diagrams. In this session, we will clearly understand how the magnetizing current, core loss current, excitation current, and the referred secondary current combine to form the actual primary current of a CT. We will also see how these vectors help us identify the ratio error and the phase angle error in a current transformer. Let's begin. This is the x-axis. This is the y-axis. See, this is the magnetizing current, IM, received by the current transformer from the supply at the primary side to magnetize the core. Obviously, it is purely a reactive current. Also, there is another current that will be consumed due to eddy current and hysteresis losses of the CT core, and this current is IC. So when we connect the CT in series with the line, and the circuit current flows through the primary of the CT, that current will also have to contribute the magnetizing current and the core loss current. The vector sum of these two currents is I0. I0 is called the excitation current of the current transformer. This is nothing but the vector sum of IM and IC, so we can write I0, the excitation current, equals IM plus IC. Now say IS is the secondary current and the CT has a ratio, say N. So obviously there will be a primary current that actually transforms to the secondary current IS, and the phase difference between that primary current and this secondary current is exactly 180 degrees. It is better to say this current is the secondary current referred to the primary, and the secondary current referred to the primary is the theoretical current that is ideally transformed to the secondary. So we can draw that current exactly 180 degrees apart from the secondary current. And obviously, this current will be N times I sub S. So I sub 0 is the excitation current which is consumed to excite the core of the transformer, meaning to magnetize the core along with its loss component. And NIS is the secondary current referred to the primary, or better to say, the NIS current is what actually transforms to the secondary circuit of the current transformer as IS. Therefore, the total primary current will be the vector sum of these two components. Let us draw the actual vector sum of these. This is the actual current IP. That means we are injecting this current IP into the CT, and a portion of this primary current, that is I0, will be consumed as excitation current of the CT, and the rest of the current will be transformed to the secondary. So officially or ideally, the ratio of the CT is NIS by IS, meaning IP prime divided by IS, where IP prime is the ideal primary current. But practically, we get the current ratio IP divided by IS because IP is the total current we are injecting into the CT primary, but the actual current transformed to the secondary is I prime P. So the difference between the ratio IP over IS and I prime P over IS is IP over IS minus I prime P over IS equals IP minus I prime P over IS equals IP minus N times IS over IS. This is the ratio error. If we want to represent it in percentage, we can write percentage ratio error equals IP minus NIS divided by IS N times 100. This means the ratio error with respect to the rated ratio represented in percentage. 1% ratio error means the ratio of the CT may differ by only 1%. This angle is theta. This angle theta is the angle between the actual primary current and the ideal primary current. That means the phase has been displaced between the actual primary current and the measured primary current, because NIS is the measured primary current and IP is the supplied primary current. Theta is the angle between the measured primary current and the actual primary current. So theta is the angular error or phase angle error in a current transformer. This is how the exciting current, the referred secondary current, and the actual primary current create both ratio error and phase angle error in a current transformer. Understanding this vector diagram is essential for grasping CT performance in metering and protection applications. Thank you for watching. If you found this explanation useful, do like the video and subscribe for more detailed electrical engineering content.